Okay, so hello everyone. This is actually the first webinar we organize on this topic at CERN. This is the first of a series. We'll start regular sessions like this weekly on Wednesday 2 p.m. I'll just share the slides. Okay. And I guess you can see the slides well. Okay, so the first topic that we'll focus on today is Kubernetes and high availability. We've been running Kubernetes for quite a while now at CERN and have some experience with this kind of things. So we'll also mention a bit how things have evolved on how we offer the service in on-premise. So the webinars will start today, and they will always be on Wednesdays at 2 p.m. Central European time. They will be live on Zoom. Everyone can join, so you can pass the link, feel free. We'll be recording them. You can find the agenda and the recording links in this link here. The topics that we are hoping to cover in the next couple of sessions. The first one is this one, availability of both services and control plane. Next week, Thomas Hartland will be talking about cluster autoscaling, and then we move to the first use case where one of the storage management systems that we have here called Wrapup is used by multiple experiments at CERN, and they will describe their experiences moving from production to Kubernetes. And then the speakers will be changing for each webinar, but we'll cover containerization and image best practices, monitoring of clusters, Prometheus, Helm and Flux, debugging, and also a nice use case of how we manage OpenStack itself with Kubernetes. So a bit about me. Today I'll give this talk. So I'll introduce myself a bit. And I'm a computing engineer in the CERN cloud team. I've been at CERN for a few years now. I focus mostly these days on containers, Kubernetes, and networking aspects of our cloud. I also work on integrating accelerators, and I'm interested in also support machine learning workloads. I previously worked on storage systems and also the grid computing system we have to process the Large Hadron Collider data at CERN, and with our collaborating sites. You have some references here. If you have questions, feel free to reach out. I'll jump to the topic today. So I went straight to Wikipedia to get this, and I thought it was a good start to define what high availability is and what we understand by it. Okay, just trying to get rid of this bar here. Okay, hopefully this is better. Okay, so, and the question, if we look at what high availability is defined in Wikipedia, we have it defined as a characteristic of a system which aims to ensure an agreed level of operational performance, usually uptime for a higher than normal period. So it's kind of more than the basic availability, but it's more than just uptime. It's also making sure that you serve as many users as possible, even when you have some partial downtime, that you can stay available for the largest fraction possible of your users. So we can think of a couple of questions we can ask ourselves about our system, and in this case, a Kubernetes cluster, to evaluate how high level our deployment is. So if we think, can my control plane for the Kubernetes cluster survive losing one master? Can actually survive losing a full availability zone in case we have multi-master clusters? And then this is for the Kubernetes control plane, and nice separation here is the availability of the control plane, but also of the applications running there. So if we think, can my application survive losing one node in case we have multi-node, then probably yes. And then can it survive losing one availability zone? So to answer these questions, we can think that the top two for the control plane, we can think of multi-master clusters, and that the masters are split across multiple availability zones. And then for the questions regarding the applications, we can think of some constructs that Kubernetes offers us like replica sets and deployments using replica sets service that gives us the in-cluster load balancing, and then some constructs like defining anti-affinity between pods and nodes, and more recent constructs like topology spread. This is kind of describing to Kubernetes how multiple replica applications should be spread across the cluster. Other questions: can my control survive a bad upgrade? So even if you have a multi-master, if you somehow have a very bad upgrade that breaks the master connectivity, etcd would be a good example of what can go wrong. Can it survive? Is the service still up if you lose the cluster completely? And then can my application stay up during upgrade? So a very naive upgrade might just replace all the replicas with a new version, which means that they might be all down at the same time, which means you would lose availability for hopefully a short period, but you would still lose it. And then is my application actually running as expected? It might be that it's running and Kubernetes would think it's okay, but actually it's just giving wrong answers or errors. And then is my application ready to serve traffic when I deploy a new version? Is it immediately put in the load balancer, or is there some initialization that we have to integrate to start serving traffic? So for this also, we have some options in Kubernetes. So for the first one with bad upgrade, one option is to treat clusters as cattle and to have multiple ones and just load balance the traffic between the two clusters with an external load balancer. And then for the questions below regarding the application, we have very cool constructs like pod disruption budgets that tell us how much an availability we are able to handle for an application, for things like upgrades, for example, and defining liveness and readiness probes. So I'll go through these slides quite quickly, and then the demo will hopefully give a much better view of all of this.
We have a question now.
Yep.
Hand, do you want to take it now?
Yeah. Go ahead.
Go ahead, Jan.
Hello?
Jan, you can talk. Jan?
Okay, maybe we take it at the end then.
Sorry for
okay.
The
yeah.
I can cut this from the recording.
Hello? Can you just mute Spears and I keep going?
Yeah.
Okay, cool. So then it's quite important to offer all this functionality. We need to make sure that the infrastructure supports all these complex deployments. So in the case of CERN, where we are deploying, our private cloud has 3 different availability zones. We call them CERN, Geneva A, B, and C. And then these availability zones offer a nice level of isolation in terms of compute. So nodes and racks are split across. But actually, we don't follow this split in all the layers. The networking layer we just rely on the level of redundancy that it offers across the data center. And then the storage is similar, although this might change in the future. But for now, we also rely on the level of redundancy that the storage system itself gives. So this is quite important to understand not only like how you're splitting workloads, but what's the level of redundancy that each of these layers is giving you. So for this, we rely on OpenStack for the deployment of our private cloud and also for orchestrating our Kubernetes clusters. We'll see quite a bit of this. And then Ceph for the storage. So I'll jump straight to how you create clusters at CERN. So the very simple setup is to have one master, one node. We have a way to define templates of clusters. So that's what I describe here as Kubernetes 1.18.2-2. And you just trigger one command and the system will do the orchestration of the cluster for you. So if you have one master, one node, obviously no high availability at all. Then we have the second option, which is to have one master, multiple nodes. In this case, we can survive one or more nodes dying, and your application will stay up if it has a replica set properly defined. But you can't guarantee that the full AZ going down will still allow your application to continue serving traffic. So the next step is to split the nodes across availability zones. At CERN, with this system, we have the possibility to create what we call node groups, which are very similar to node pools if you are used to GKE. And here, when you create a node group, you can actually specify which availability zone that node group nodes should go to. So in this case, availability zone A, and we'll create similar ones. I'll show this. In this case, we can survive a full AZ going down. And then we start talking about multiple masters. In this case, we still we have improved the availability of the control plane because we have multiple masters. But to have high availability, we need to have also the master split in multiple availability zones. This is a very simple example. What I will do is I'll switch to the demo, and I'll try to show you what I can do here. Can you see my screen, Spiros?
Yes.
Okay. So I'll start by showing you what I mentioned before, which is this this possibility of having templates. So this is how we offer, and you will see that we actually offer multiple versions. Here I'm selecting only 118. We actually have to split today if we want single master or multi-master. This requirement will disappear. And then when you create a cluster, you have a command for that. And you have a bunch of options. The first one is, of course, the cluster template, which is required. And then you can pass some labels that add or disable features as you wish. The number of masters, number of nodes, and then the flavor for masters and nodes. And there's a couple more options that you can also use. I'll show you two clusters that we'll be using today. So one is seminar single 01. And just to show you how once we deploy it, we see that it's deployed. And you can see that the node addresses, we are using 2 nodes. And in this case, we have a bunch of flags. It's not really relevant right now. In this case, we have a single master. And we can also see the API address for the Kubernetes cluster matches the master address, which means we don't have a load balancer in front of it. And if we go for the second cluster that we'll be using today, then there we'll have this multi-master capability and also a load balancer. So we have a lot more nodes that will be split across AZs. We have 3 masters, and note that also the API address is now it's the IP of the load balancer, not the IP of any of the masters. So it's just load balancing the traffic between the masters. So that's pretty much it for this part. And then what I will show you here, because this is also relevant, now we stop about the, we went through pretty quickly on the orchestration of Kubernetes clusters, but now we have to talk about high availability also of the applications inside the cluster, and Kubernetes offers you several possibilities. So if you've used Kubernetes before, you know that you have a deployment that has multiple pods and a replica set. And then if you want to expose the service, you define a service resource. This service can be of 3 kinds. The first one is what's called cluster IP. In this case, the service is only available inside the Kubernetes cluster. We see here, we have a service construct that then redirects to 3 replicas of the service, each one served by 1 pod. If you want to expose this service with cluster IP, you cannot really do it easily. All you can do is create a proxy between your local machine, where you have the Kubernetes client and all the credentials, and you create a local proxy between your machine and the service you want to access, and you can access it in localhost on the port defined. So it's not a very practical way to offer to end users, but it's useful if you want to test something with your machine, or just access a service that you don't want to expose. The second option is called node port. So in this case, we have a service and 2 pods, and each pod is in a different virtual machine. And what we do is we expose the service as a specific port number, and this port will be exposed on the virtual machine itself, and then the traffic redirected to one of the pods. So this is what we see here. The traffic comes from outside. You can contact any of the nodes in the cluster. All of them will have this port that you chose open, and this port will always serve the service that you defined. I'll show an example in the demo. And then the ideal situation is that it's very similar to the cluster IP situation, but instead of having a proxy, you just register a service in an external load balancer, and this load balancer will know how to route the traffic to your cluster. So this allows you to expose the service to an end user with a real IP, and the load balancer will route the traffic to your cluster, and then this service will do the in-cluster load balancing between the multiple replicas. So these are the 3 service types. and the way that you can expose your services to end users. An interesting concept is also Ingress. So it's not a service type, Ingress. What Ingress does is it allows you to have one controller inside the cluster that redirects traffic to multiple services. And you can define the rules that are used to redirect to different services. So in this case, I'm using two different services, one that is redirected based on the DNS foo mydomain.com, and another one with mydomain.com/par. And it goes to the two different services. The controller runs inside the cluster, and the way you expose this Ingress controller to the end users can be different. So you can actually use either a node port, or you can also register in an external load balancer as well. So this is a very quick overview because we'll jump to the meat of things in the demo. So I'll try to show you again. I'll start with this single case. So I'll show you again what the cluster looks like. So we'll be playing with this cluster that has two nodes, one master and no load balancer, so no multi-master. If I do a get node here, we can see the same. So we have our master and two nodes, and you can see that actually the master is in one availability zones, and the nodes we were unlucky, so we ended up with both nodes in the same availability zone. So for this demo, what I will also do is I'll keep 3 terminals here, and I'll show you. Yeah, so I'll do something where we'll use a very simple Nginx application. The Nginx application will have multiple replicas. So in the top terminal, we'll be monitoring the deployment of this application. And then in this middle terminal, I'm actually doing a curl on one of the nodes and querying in the node port. And this is just the HTTP status code, so it's 000, because there's no reply right now. But hopefully when we have the applications running, we'll see 200 OK here. So I'll show you first the service. So we mentioned that the first one of the kinds of service types of services is node port. In this case, we are exposing a given service in the cluster using a specific node port that we chose here, 30887. And this is what we are querying in this terminal in the middle. So hopefully at some point we'll have it. And when you select the service, you also select the labels that it should match the replicas. So anything that has this app Nginx will match this service and will be a valid replica to serve it. And then our actual service is this one here. So it's a simple deployment of an Nginx component. We'll start with 2 replicas. Again, we see that the deployment has a similar match to the service, and then we define the pod here with a simple container, Nginx listening on port 80, 2 replicas. So I'll apply this. Okay, so we see that the pods are already being launched, and pretty quickly we have 2 replicas running, and we start seeing the traffic being served with this 200. Here, we can also see how this looks. So we can see that, in fact, we have this service type node port. And if we describe it, we can even see which are the endpoints that are being served. So we have 2 replicas. Each one has an internal IP in the cluster, and we are serving the service in this port here. Now you saw that also that the launch was very fast, like in just a couple of seconds, the service was running. This is okay, but in some cases, as we discussed, we might need more than that. So we might need to describe some conditions and some tests so that Kubernetes knows when a pod is ready to serve traffic. So the first probe that we will define here is this liveness probe. So the liveness probe is periodically doing some kind of test against the replica, the pod. In this case, we are using HTTP. You can also use like a shell command if you want. And we are testing that the reply on / is giving a proper HTTP code. A very common pattern is to have actually /health that does a bit more than just replying with the default page. In this case, we are just doing that. And it's doing it every 3 seconds. So it's pretty reliable. The second one that we saw is that the case that you deploy a new application or a new replica, but actually there's some initialization step that is required. So we give it this readiness probe before the pod starts serving traffic and is included in the in-cluster load balancer. And this is called a readiness probe. And it's we can actually introduce a delay also for when these probes run. So that's what I'm doing here. I'll change this. And now I'll redeploy. So just wait that the application is gone. We can see that the code is 0 again because we don't have any replica serving it. I deploy it, and now you can see that the containers are set as running. We still have 0 because we have this probe that is still not ready. So I set for 10 seconds. So in a bit, we should see here the ready going to 1. And we start having a 200 HTTP code. So this is quite important. If you want to do highly available applications, you have to make sure that all these settings are properly defined. Now the other detail here is that we have 2 replicas, and you can see that they are spread into different nodes, node 0 and node 1. If we go back to our description here, you can see that I defined what's called an affinity policy, and I defined it as an anti-affinity. So it's a pod anti-affinity. I say that this anti-affinity rule, this affinity rule is required during scheduling. So the scheduler has to comply with this for all replicas. I say which pods are affected by this. So any pod with a label app matching nginx. And then the most important, the topology key. So I say that this is actually an anti-affinity rule that should be applied for hosts, so nodes, basically. So that's why we end up with this split of replicas in the 2 nodes. So let's try to increase this to 3 instead. And I update the deployment. And we can see that we have now a new replica here. It's in pending state, and it's not being scheduled. And the reason is that we set this anti-affinity rule that says it's a hard affinity, that no 2 pods of this kind should be running on the same node. So this means that we don't have a node where we can schedule this right now. We can actually get a detail about, get some details of why this is happening. So if you ask Kubernetes why it is not scheduling, it will tell you here that 0 out of 3 nodes are available. 2 nodes didn't satisfy the anti-affinity rules, which, so it's saying 3 because there's a master as well, but basically cannot do anything right now. It's a bit stuck. So what we can do about this is, I'll actually delete this here, and I'll show you something we can do about it. So this affinity rule that we defined is required. So we can change it so that we instead say that we prefer that the replicas are running in different nodes, but we actually don't mandate it. So this is the second rule that I have here. So in this case, we say prefer during scheduling, and the rule is exactly the same. The topology key is the same. So in this case, if we apply again, it will redeploy with 3 replicas, but you can see that in fact, now we have 2 replicas in node 1 and 1 replica in node 0. And because we allow this now. If it had 3 nodes, then the scheduler would prefer to split the 3 different nodes, but it cannot do this. So it just decides to do this. So now we can start playing with the actual higher availability. What happens when we start breaking things? So here we have the HTTP code being 200. It's load balancing between the 3 replicas, and we also see that we have this. All these nodes are ready and working. So we'll try to simulate. Let me just check that I deleted this properly. Good point. Okay. So we'll start by trying to simulate a failure, and to do that, we'll drain one of the nodes. So we'll actually drain the node with most replicas. Like draining is kind of a voluntary action, but it can simulate like what happens if two nodes would go down, or 1 node would go down in this case. So I'll drain this. I'll drain node 1. We have 2 replicas there, and note how it reacts to this. So it killed immediately the 2 nodes, and now we have the 3 replicas going to the other node. Yeah. So it kind of recovered pretty fast to do this. So that's quite nice, but I don't know if you noticed that it was a bit too fast that it did this, meaning that it killed both pods at the same time. What that means is that we actually lost 2 out of 3 replicas for a certain time. So we lost 66% of our capacity for a couple of seconds. So one option that we have is to, instead of doing this, we can instead add what's called a pod disruption budget. So to do that, I'll show you here. So there's a construct in Kubernetes called the pod disruption budget that basically allows us to define what are the conditions, what is the state of the application that we allow in the worst case. So in this case, we say that max and available should be 1. We shouldn't have more than 1 replica out of the ones we want unavailable at any given time. You can also express it using percentages, and you can express it in the other way, saying mean available, for example. And again, we use this selector to match the appropriate pods. So let's create this now, PDB. So now we have this pod disruption budget that it's max and available. Can actually describe it and see that currently we have 3 replicas. The desired minimum is 2, so we are okay. It's happy. It allows disruptions. It can kill 1 right now. So if I get node, just to try to simulate this now, I'll cordon this node again, and cordon, sorry. To get the node back, I'll delete this, this application. Yep. So we should be good. I applied. Again, we see now that we have 2 replicas in 1 node and 1 replica in this second node. All nodes are available. And now I'll drain again, but I'll drain the one that has the most replicas, so the other node now. All nodes are ready now. So I'll drain this, and you will see the difference. So instead of killing like 2 in a row, what it will do is it will kill 1, and it's giving me a message saying that it cannot kill the other one because it would break the disruption budget that we defined. So actually it has to wait that this new replica is ready to serve traffic to finally then go and kill the second pod. So it's going now second pod. So it's allowing us to do this gradual move. You can see that in this case I'm draining, but actually if you would be doing an upgrade, it would be exactly the same. It would do an upgrade, like a controlled upgrade, so that you don't just kill the service. You lose a lot of capacity in one go just because Kubernetes is really fast doing these things. So it's good to define this this kind of concept as well. Yeah. So then we'll do something here. We'll change it back to required. So now I'm changing the affinity between the pods back to required. So we don't allow this this possibility of, sorry. I'm putting the cluster back in the same state. Already, all nodes are ready, and now we put back the affinity between the multiple replicas to required. So we have a hard affinity again. I'll recreate the application. So we have again 1 here, 1 here, and then we have 1 pending because we have a hard affinity, and as we saw before, it cannot schedule it. So what happens now if I lose 1 node? So let's say we would lose node 0. Remember, we have this pod disruption budget saying that we cannot go with more than 1 unavailable. And in fact, right now we have 1 unavailable because it's in pending. So let's try it. So actually, it's not allowing me to evict the pod. If you would be doing an operation in the cluster and it would go below the pod disruption budget, it's just not doing anything. And this, it just keeps telling you that it won't be allowed to do it, which means you have to do some kind of manual operation. You define the rules that the minimum you need to serve an application is this. So it will need some kind of operator's intervention to either increase the size of the cluster or change the affinity rules or something temporarily. It's quite nice because it just allows you to express this in a very simple way. And that's pretty much it for the single master demo. So now we'll go change to a slightly more complex setup where we will have multiple masters. So I'll just reconfigure here my terminals. So we'll use exactly the same application. So I'll do the same curl commands as I was doing before. It's again listening on the same node port, just a different cluster, and the cluster will also look slightly different. So let's start like before. We describe the cluster. Okay, so now we see a bunch more nodes. We see the same flags that we talked about, 3 masters and the API address. So that's the important part. So we are using a load balancer to access the control plane. So if I do a get node, actually, so because we have this load balancer, I also want to show you. Internally, we have a load balancing service. So when we define that we want multi-master and that this should be doing creating a load balancer, external load balancer. So this is creating an external load balancer in our cloud. We also rely on OpenStack and a tool underneath called Tungsten Fabric to provide this functionality. And we see that we actually create 2 load balancers per cluster. So this is my backup cluster, but 2 load balancers. One is for etcd, and the other one is for the API. So it's actually, it would be a nice improvement to start requiring only 1 load balancer to save resources. Each one has a virtual IP, and you can see that the one serving the API is 6.23, which matches what is here. And then in the config file that I'm using to access the cluster, the server part is also configured to use that load balancer address. The load balancer behind, so each load balancer has a pool. So if I list the pools here, if I go to the API pool, I can list the members in the pool. And there will be 3 members because the 3 members of the load balancer are the 3 master nodes that we have in this cluster. So it matches the list that we saw before. That's the OpenStack part for the provisioning. And now if we look at Kubernetes, then we can see that we have these 6 nodes. So we have 3 node groups. So one thing I didn't show you that I can actually show you is, I did a cluster show here. But actually the way this works is we split in this cluster, we have several nodes, but we actually also define these node groups, what I mentioned earlier about node pools, equivalent of node pools in GKE. And we define a different node group per availability zone with 2 nodes each. So we have 6 nodes split, and then we have the default node groups that are for the master. And we actually have a default with 1 node there, but I disabled. So if we look at the Kubernetes equivalent, we see that in CERN Geneva A availability zone, we have 2 nodes, 2 in B, 2 in C. And actually, this is a bad example because the 3 masters are in the same availability zone. So this is a feature that we are just about to deploy, which is the ability to split the masters across availability zones. Right now, you have to trust in luck, which is pretty bad, but we are just about to have this proper. It's not a big change. But in most cases, what you do is you deploy the cluster a couple of times until you have a split that you like, but this is just about to be improved as well. In a multi-master cluster, there's a couple more things that are interesting, namely the DNS. DNS is always the source of a lot of limited availability incidents. So we use core DNS, and you can see that we have here 2 instances running of core DNS, 2 replicas. And we actually have something called the kubedns autoscaler that will scale up and down the instance number depending on the load. And then the last bit I'll show, because I still have a bit of time here. I'll show you what in the master it looks like. So people at CERN actually have access to the masters, for now at least. We run everything containerized, so it's a Fedora core based deployment, and you can see that even the base services are running containerized. So if I go and I just log into this pod that is running it etcd, login, I get a shell here, and I can see etcd-ctl cluster health. You should see 3 instances, so that's pretty good. And you can also do member list if you want to check details. So we have the 3 masters listed here. So we have also, it's quite important also to know that etcd, if you look at the documentation, it uses raft underneath. So you need to have an even number of instances. So if you have a cluster with 2 masters, actually etcd won't be highly available because only 1 will be in the cluster at each time. You need 3 to get the quorum. And then if you go to 4, same, you have the equivalent of 3. There's no point in having 4. 5 is an improvement. So that's quite relevant as well. So if I go again to get nodes, and now what we will do is we'll play in the same way we did for the previous cluster with single master. We'll try to create some problems. But because to make it a bit more interesting, I'll show you that actually there's a slight difference in this setup. So before, this looks all the same. We have a deployment, an Nginx application. We are actually creating 6 replicas because we have a larger cluster as well. The selector looks the same. Everything looks the same. The liveness probes, exactly the same. Now, when we get to the constraints, I wanted to show something different. Before we use this affinity rules, so anti-affinity and affinity, you can define, and you can define if they're preferred or required in scheduling. There's a limitation on this. As you saw, if we do an anti-affinity for a pod, it just says I cannot have more than 1 replica in each node for this pod, for this type of service. Sometimes you want to have a bit more, a better way to express this. So you want to say, okay, I can have 2 in 1 node and 1 in the other, but not more than 1 difference. And this is this skew. So to do that, instead of using affinities, there's something called the topology spread, which is used to be called even pod spread, I think. It's already enabled by default in Kubernetes 1.18. And here you have a bit better way to like say what you need in the cluster. So in this case, I'm doing actually 2 constraints. I'm saying that regarding zones, I want to have a spread constraint, and I'm saying that when unsatisfiable, should not schedule. And I'm saying that the max queue is 1, so basically even spread. And then for the hosts, the topology key here is host name, like before I had in the pod anti-affinity, and again the max queue 1. So if I now deploy this, so quickly we see the pods creating, and we start seeing the HTTP code 200, and we see that with this spread topology definitions that I did, we have a pretty good split. So here, 2 nodes in A, 2 nodes in B, 2 pods in B, sorry, and 2 pods in C. So that's pretty much what we want to have. So let's try to now create some trouble. We'll drain one node. So in this case, we'll drain, sorry, again to try to simulate a failure. So we'll drain the node 0 in availability zone A. So let's see what happens. So basically, it killed 1 pod. Well, it killed. It's actually killing both. But you can see that now it says the replica goes to pending. So you can see that the replica that was running in node 0 in the availability zone A is gone. It tried to create a new one, but it's in pending because it cannot comply with the topology constraints that we added that say that there should be no difference between the balancing across nodes and zones. So if we do a describe of this pod, we should say again, Kubernetes is nice enough to tell us that that it couldn't find a node that matches the topology spread constraints. Yeah, so then let's delete this. And now we'll try to see what happens if we change topology spread constraints. So in this case, what we will do is we'll change the node constraint, saying that we now allow a max queue of 2. So we are more flexible in terms of splitting things across nodes. So if I apply again, now you can see that it's actually deploying.
There is a question, Ricardo, if you pick.
Yep. Go ahead.
I can read it out because it's typed. Which are the benefits of using these topology spread constraints instead of pod affinity, pod anti-affinity?
Right. So that's exactly this is it. In pod affinity, anti-affinity is just hard or soft. You either do not allow that more than one pod is in each node, saying that pod anti-affinity, you can only have one replica in each node, and that's it. In topology spread constraints, you can actually define this queue that says, okay, I can have an unbalance between nodes of 2 in this case. So I allow a difference. If you look at the documentation, there's a simple formula, but basically you're not doing hard and soft. You can actually have this middle term where you can have a slight unbalance between the two. I think that was it. Okay, so in this case, that's what we are seeing here. So actually, we changed this queue, and now we have 2 replicas running on the same node. So we still have this skew of 1 across availability zone, saying that we have to have the same number of replicas in each availability zone. But per node, we actually allow one node to have 2, even if all the others have only 1. So there's this skew that is possible with this kind of. This is not possible with the affinity policies. So yeah, that's I'll delete this. And now I'll try to do something else, which is I'll change the host. Well, I will skip this part, but or I can do it. So another option is, one is to increase the skew, as I did here. The other option is to do to change the when unsatisfiable rule. So you can say when unsatisfiable, just schedule anyway. So this becomes like a soft constraint like we had before. So this is an option instead of the skew. So I can change it back to 1. Well, it doesn't matter really. I can also leave it at 2, but I'm saying schedule anyway, and it should just work. So if I apply again, we end up with the same setup. So now what we can try is also to simulate a full AZ failure. So in this case, I'll uncordon. So we have all the nodes back. I'll update to what we had it before, just to show you. Do not schedule. I'll delete it quickly. So I'll just recreate the initial setup we had, where we had perfectly balancing between nodes and regions. There we go. So we start serving traffic. This should change to 200 very soon. Actually, running the wrong commit. Okay, there was some glitch there. It's 200. And we have a proper spread of the thing. So we will now try to simulate a full AZ failure by basically draining both nodes in the availability zone A. And let's see what happens. So it terminates the first one and creates immediately a pending replica here. And then it will also try to do the same for this one. Yeah, there we go. So it terminated both pods in availability zone A. And now you can see that we have two pending replicas. And the reason is that we still have this constraint that things should be balanced across zones. If we would add, and we can't basically add any replica to this availability zones here. So we can also update that topology constraint. And this is the zone one now. So we'll do schedule anyway. And we'll do host 2. And now we actually apply. So when I apply, it also creates a new replica set. So it will be reshuffling a lot of things there. But basically, the goal is that we don't have availability zone A, but we need 6 replicas. So the goal is that we end up with 3 replicas in B and 3 replicas in C. So if this one, yeah, there we go. So basically, Kubernetes just reshuffled the replicas. We made this constraint soft. So we now have this setup here, which is what we need. And this is, again, quite easy to express. And like during all this time, thanks to the load balancing internally also, we always had uptime for our users. Okay, so the last demo I want to show today is a load balancer service. So we mentioned before in the slides that the third type we mentioned there was a service of type load balancer. This means that it will actually create a load balancer endpoint on an external load balancer service. In our case, we have an internal one on-premise, but it's external to the cluster. So there's some things we can tell about the load balancer. So in this case, we say in which network inside our data center we want to create the load balancer virtual IP. And then we say the port. And we are saying that it should match, so here, it should match any pod that has app nginx. So the service we are running right now will match it. So if I create this now, sorry. And I get service. So you can see that now I had my node port service already running. And now I have a new load balancer service. And you can see that the external IP is pending. And the reason for this is that it takes a bit to create the load balancer. So now the load balancer is created. I have an IP. If I list my load balancers, I can see the 4 that I had already for my cluster and my second backup cluster. And now I have an extra one, which is for my service here. And the IP address is a virtual IP that matches the external IP here. So here I'm curling for my service using a node port and a VM, but actually I can try to just do the same by using the IP that I just got now. And I can see the reply from nginx. So we are all good. And I think that's all I have today. I already went 50 minutes, so I'd like to leave at least 10 minutes for questions. So I'll just show you because this is a bit more basic and everyone is used to it. So there's the last bit that I mentioned in the slides is the possibility to create an ingress. So in this case, we have a service of type cluster IP, and we want to expose it. So one way of exposing the service instead of using a service type load balancer is to have an ingress, and you need an ingress controller running in the cluster. In our case, we support traffic and nginx, so I'm choosing traffic here. I'm saying that it should be exposed in HTTP and then the service port. And basically that's it. And then in our case, there's different options for the setup of the Ingress controller. But in our case, we're actually using node port and then DNS-based load balancing between the VMs that have the controller running. You can also use an external load balancer if you prefer. So that was for the demo. And so I covered some of the topics about higher variability. There's a lot more about this topic. Some interesting parts would be to talk about stateful workloads. If you want to run like a distributed database, for example, it's a very interesting because the management of stateful applications is quite different. So it would be interesting to cover that and implications in high availability. And then storage provisioning and access is also something quite relevant. There's a lot of work going on upstream in the Kubernetes community about multi-cluster service and how this can be integrated into Kubernetes itself. People are doing this in many different ways, but often it ends up being an external load balancer somehow. And then the reason I didn't go into a lot of detail in Ingress is that it was just made GA, generally available, but actually it's about to be, the reason for that is that it's about to be replaced with something else. So this is, there's ongoing work to define this gateway class and route. You can search for details online and follow in the community if you want to contribute with comments. It's quite interesting work of what's coming next. And with that, I finish, and I'm open for questions if there are any. And I think Spiros will moderate.
No questions yet.
Feel free to raise your hand if you want to ask a question, or just type in the questions and answers. And if there are no questions, then we'll just wrap it up.
Nothing yet.
Okay. So is there anything else, Spiros, that we could talk in the next high availability related talk?
I think the subjects that come after will be covered more or less by the monitoring part. So, okay, you have all of this, what extra monitoring you need, where is my traffic coming from, but I think we have it scheduled already.
Yeah. Yeah, I think the stateful workloads is the one that is less common than this kind of stateless deployments. And yeah, for whoever is running databases inside Kubernetes clusters or Zookeeper or something like that, it's quite interesting to understand what are the failure possibilities as well. Okay.
I think that's it.
So if there are no questions, then, well, next week we have another talk by Thomas Hartland, and it will cover the cluster autoscaler that we have deployed at CERN and how we are using it. So hope to see you all there, and we'll upload the recording soon and make it available. Thank you very much.